Hello, everyone, and welcome to the Joy of Abstraction Book Club, Chapter 24, and the Epilogue. It's the end. We made it to the end. Well, we've nearly made it to the end. We've actually got 29 questions on this chapter. I'm so happy that there are so many questions on this last chapter and that so many people have made it to this point. The sun is shining in Chicago, so I've decided to do this video outside again. It's the last one. It is warm, sunny, bright. I'm squinting. There's traffic in the background. I can't really see my screen, but I've just decided I'm going to do it anyway. So let's get started right away. Higher dimensional category theory. My specific field of research, my favorite thing, one of my favorite things. And so here we are. First question. To learn more about higher dimensional category theory in full detail, is it necessary to first fully master all of the lower dimensional material? Well, no. I mean, you can always learn more about something without having fully mastered the earlier things. In fact, I think it's really important in all of mathematics to be ready to move on to something else before you fully mastered something, because you can never fully master something. If you wait until you fully mastered it, then either you'll never fully master it and so you'll never move on, or if you think you've fully mastered it, you're just wrong, because I don't think there's any such thing as fully mastering everything. And so I sometimes think of it more like pulling a suitcase along by a piece of elastic, where there'll be a delay when you're tugging on it, and then sometimes it'll ping forward, and then there'll be another delay, and it doesn't really go consistently. Sometimes you can work really hard at something and not feel like you're getting anywhere, and all you can do is keep going, and then perhaps in retrospect you'll understand that earlier thing later once you've kept going a bit. I think it's definitely, it's usually, typically, often, probably a bit futile to try and fully master something before moving on to something else. So the next question is, when thinking about higher dimensional geometry, some of the intuitions from lower dimensions have to be abandoned. Do we have to do something analogous for higher dimensional categories? I don't know. I mean, it depends what your intuitions are, right? Everyone's intuitions are different. And I think I really try to approach lower dimensional category theory in a way that develops the right intuitions for higher dimensional category theory, because if you do it right, it's really the same intuitions. And I think that that's a lot of what I say all along, is with the higher dimensions in mind, things like knowing exactly where you're invoking certain things, so that when you go into higher dimensions, you know where you have to be careful, and knowing where you have invoked an axiom. So for example, knowing where you've used associativity, so that when you go into higher dimensions, you can just turn that into an isomorphism instead of an equality, rather than just thinking of the associative, the different associations of things as being actually the same. So the next question. There are some questions that I had some difficulty understanding. My psychic powers may be failing me. One says, I understand that weakening can be using isomorphism instead of equality. Yes, that's typically what weakening means, and then going further into weaker and weaker notions of equivalence. What's the difference between having weak vertical composition only versus weak horizontal composition only? And there's another question that says, what's an example of when you would only need weak vertical composition for a phenomenon you're trying to model? And I'm a bit confused about this, because I don't see a place where I mentioned weak vertical composition versus weak horizontal composition in this book. Now, it's true that I have some recent research papers about it, and so I'm wondering if someone is asking questions about those. I don't know an example when you would need only weak vertical composition for something you're actually trying to model. The reason that I study those things is for theoretical reasons, to understand where coherence is coming from. The difference between having weak vertical composition only versus weak horizontal composition only, I don't know what to say about that, because the difference is that they're different. Those are different types of composition, and if you have weakness in different places, then it will be different. So another question about horizontal and vertical composition I don't quite understand. Is vertical composition always favored over horizontal composition? I don't know what that means. They're just different. They live in different places. They do different things. it's not that you have a choice about which to do, really, they just are different. And the next question, what is the rule to decide whether to go with vertical or horizontal composition? I also don't really know what that means, because they live in different places. And so if you can compose something vertically, then you can, because that's when the one cell boundaries meet up. If the one cell boundaries don't meet up, then you can't. If the zero cell boundaries meet up, then you can do horizontal composition. If you're trying to make a structure and you're trying to encode something as vertical or horizontal composition, then it just depends what the structures are you're trying to compose and what bounding dimension you're trying to stick them together along. Another question, does there tend to be only one notion of composition at a given level? Vertical for a Hom category, but horizontal for two cells in the enriched 2 category. So there tends to be as many notions of composition as you have dimensions available, because there's a notion of composition for each possible boundary dimension. So if you have 2-dimensional things, then there will be 2 ways of composing them. If you have 3-dimensional things, there will be 3 ways of composing them. So in a Hom category, that's a category. That's a 1-dimensional thing, so there's only one way of composing. But for 2 cells in a 2 category, that's 2-dimensional, so you do have 2 ways of composing them. Gosh, it's really hot in the sun, it's lovely. I know that a lot of people don't like the sun and love it when the sun goes away for the fall, but I love the sun. And I don't like the fall because the sun goes away and it becomes cold and the leaves die. And I don't like dead leaves. I don't like death. The next question. I was under the impression that equality was too strict for category theory, but now we have the notion of sameness for 2 categories. How should I be thinking about equality and sameness? Well, sameness is a much more general term. It's not technical. And the whole point about sameness is that it has the space to be weaker than equality. And so the reason I use the word sameness is to give us the space to say, oh, we're going to do something more nuanced than equality, because we can have isomorphism or equivalence, and all of those things are notions of sameness. And then what sort of equivalence do 0 cells have? Are the 0 cells in a 2 category always categories? No. The 0 cells in a 2 category can be anything, just like the objects of a category can be anything. But just like one of the motivating examples of a category is the category of sets, one of the motivating examples of a 2 category is the 2 category of categories, functors, and natural transformations. And so in that particular 2 category, the 0 cells are categories, but in general, they can be anything. And the 0 cells of a monoidal category can also be anything, as long as there's some kind of tensor product on them. And then regarding what sort of equivalence 0 cells have, well, they have equivalence that's 1 level weaker than isomorphism. So isomorphism says that there's a morphism going this way and a morphism going back, and they compose to be identity. Equivalence says there's a morphism going that way and morphism going back. And then there's the composite isn't exactly the identity, but there's a mediating isomorphism between that composite and the identity, just like the equivalence of 2 categories, and also for the other composite. I can see vaguely in the screen that I look like I'm squinting. I'm not grumpy, I'm just, the sun's in my eyes. Right, so now some specific questions. We have 19 specific questions, which is pretty amazing. So first question, page 368. Should I be thinking categories come with functors and also natural transformations in terms of there being outside the category but contained within bigger categories? Yes, this is a zooming in and out thing. So there's an individual category, and then there's a totality of all the categories. And this relates to a future question. The totality means all of them. You gather all of them into a structure together with the higher morphisms between them. So the functors are between categories. So there's categories and functors between them that are sort of outside those categories, mediating between those categories. And then the natural transformations are also outside of those categories. But all of that stuff lives inside a two-dimensional totality of categories, functors, and natural transformations. Is the totality of sets the category set? Yes. And then someone says, what exactly is meant by totality of categories? Is it all the instances of a certain type of category? If you say totality of structures, it's all of them. The idea is to gather all of them into a structure and put appropriate morphisms between them and make it the appropriate dimension for it. So a totality of categories is two-dimensional, but a totality of sets is one-dimensional. Page 369, could you please say more about natural transformations arose from the existence of morphisms in categories? I thought we needed functors between categories in order to get a natural transformation. What am I missing? Yes, you do need functors in order to get a natural transformation. But what I mean by the natural transformations arising from the existence of morphisms is that the actual data for a natural transformation is a bunch of morphisms in the target category, right? The components of a natural transformation are morphisms in your target category. And so those natural transformations are based on the existence of some one-dimensional structure in that target category. And I think what I was saying is that therefore, if your target category has some two-dimensional structure, then we'll get an extra level of structure in between our functors. Page 370, in the definition, the arrow going between F and G looks like a natural transformation arrow, but it's going between morphisms, not functors. Is it okay to think of it as a natural transformation anyway? Not exactly, because it isn't necessarily a natural transformation. So it's just like the fact that when we draw arrows to represent morphisms in a category, they look like the same arrows we use for functions, but they might not be functions. It's just that it's inspired by functions because the category of sets and functions is a motivating example of a category. So similarly, for two cells in a two category, natural transformations are a motivating example, and they are two-dimensional. So anytime we have something that is two-dimensional, we can draw it with a double arrow. It doesn't mean that they are all natural transformations. They probably are all two cells in a two category somewhere. The implication sign is a different one. Page 370, why can't identity two cells act as identities with respect to horizontal composition of two cells? They do, as long as you're careful about what that means. And so I probably should have said that in that definition. So I've added it to the errata page. Maybe I will share the whiteboard screen now. So you just have to be careful to type check a little bit, because if you're going from A to B, then there are a bunch of different kinds of identity you can have on here, and they don't all exactly act as identities. But the one that does is if you have the identity on B as your one cell, and then the identity on B. So it's not that identity two cells act as identities, it's that identities on the identities. And that's because when you define it as a category enriched in categories, your identity functor goes to this category. And so this is the terminal category. It has only one object, which picks out an identity on A. And then it has one identity morphism, and that necessarily by functoriality picks out the identity on A. And then the identity axioms for the composition of the enriched category ensure that this two cell will behave as the identity with respect to the horizontal composition. Page 372, can you explain what the arrows 1 and id cross 1 are in the first identity diagram? Okay, page 372. Right, so this diagram says that you start with the HOMs from A to B, which is isomorphic to the HOMs from A to B. Oh no, the first one says it's isomorphic to 1 crossed with the HOMs from A to B. That you then do id cross 1, and that goes to C of A cross A cross C of A to C of A cross with C of A B, Then you do composition, and that takes us to CAB, and that this should be equal to 1. So hopefully you can see what this 1 is here. This is the identity functor from CAB to CAB. Where are we working here? Oh, this is just a category, so that's a set. These are sets and functions. So this is the identity function from CAB to CAB. Now let's look at this one. So this one, this is a function crossed with a function, so it acts on the two parts of the product separately. So the id is going from 1 to CAA, and the 1 is going from CAB to CAB. So I hope you can see that that 1 must be the identity function from CAB to CAB, which it is. And then id is defined just above that at the top of the page. It's the identity, it's the function picking out the identity. This is an A, picking out the identity on the object A here. So what this is doing, if you chase elements around it, let's chase elements in red. I think that's why we had red open from the last time. So you have a morphism here, F, going from A to B. And then under this isomorphism, all that happens is it's now an ordered pair together with the single object of the terminal set. So under this isomorphism, we end up with some random object together with F, right? Then this turns into an ordered pair where the first thing has to be, oh, I wrote my composition the diagrammatic way around in this diagram. I may have to fix that. So this picks out the identity, and we've still got the morphism from A to B, which is F here. Then this is composition. So down this way, what we get is F composed with 1A. Whereas coming down this way, it's the identity. So we just get F. And so the commutativity of this diagram is telling us that F is the same as F composed with 1A, so that this identity really does act as an identity for F. Hope that helps. Next question. Is there a reason there are no zero cells in the definition of two category by enrichment? It's just that I called them objects there rather than zero cells. So the objects there have become zero cells. Page 373. When making a category enriched in V, how do we take the first part of the identities definition out of set and place it in V when it has to pick an element from a set? It doesn't have to pick an element from a set. So when you're making that definition, the enriched category definition, the identities part says that you have a morphism from the unit object of your enriching category to the HOM from A to A, and this is a morphism in V. So this doesn't actually pick out an identity morphism, because when you're enriching in a general category V, you don't actually have morphisms, you just have HOM objects in V that we don't really think of them as individual morphisms. So this doesn't pick out an identity morphism, it's an identity acting thing. That is a slightly weird thing about enriched category theory. You do have to you have to let go of the idea of elements of sets, and therefore you have to let go of the idea of actual morphisms. Okay, page 374, could you sketch out the answer to T24.1? Oh yes, this is about the fact that functoriality gives the interchange law. I do like this. I do recommend you trying to do this yourself, because it's much more illuminating than watching someone else do it. Of course, if you're stuck, then trying to do it yourself isn't going to get you anywhere. But the idea is that we've got a composition functor going from CBC crossed with CAB to CAC. This is a functor, because those are categories. We're doing categories enriched in categories. So this is a functor, so it acts on objects and morphisms, right? On objects, it takes a morphism from B to C and a morphism from A to B, and it produces the composite, right? Now, on morphisms, these are the Hom categories of a 2 category. So the morphisms are 2 cells. So this is a 2 cell from G to G primed called beta. And this is a 2 cell from F to F primed called alpha. And what that produces is the composite, which goes from G composed with F to G primed composed with F primed, and it's called beta star alpha. Now, functoriality says we have to look at a composable pair in this product, and composition in this product happens pointwise. So a composable pair means that we have G to G primed by beta and A F to F primed by alpha. That's our first morphism in this product. And then the one it can compose with is going to go from G prime to G double primed, and that's going to be beta primed. And then it's going to go, the other one is going to go from, F primed to F double primed, and that's going to be alpha primed. So this is the boundary along which we are composing these 2 things in the product. And what functoriality says is we can either apply our functor first and then compose, or we can compose and then apply our functor. So if we apply our functor first and then compose, so this way we're going to do functor, then compose, right? So if we apply the functor, then what we've done is we've done the horizontal composition. So we do the horizontal composition on each part, and then we compose them. And the composing is vertically. Whereas this way, we're doing compose and then apply the functor. So we compose, and that means we compose inside this product. And that happens pointwise. So that means that we compose vertically, individually, and then we apply the functor, which means we do the horizontal composition afterwards. So I haven't written everything in here, but I hope this now gives you enough so that you could fill everything in and see that that is what the functoriality is telling us there. Okay, good. Page 378. Could you point out where the unit for the monoidal category is in this 2 category version? Yes. So a monoidal category is a 2 category with only 1 0 cell. So the 1 cells of the 2 category become the objects of the monoidal category. Now, the unit in a monoidal category is an object, so it must have been a 1 cell in the 2 category. And what's the only distinguished 1 cell we have in a 2 category? It's the identity, because we've only got 1 object. So it's the identity on the single object that becomes the unit of the monoidal category. Next question, page 379. In the table, is the general principle that it looks like the unique 0 cell vaporizes, great word, in the monoidal category because it's not giving any information? Yes, that's exactly right. Because it's not giving any information, we can just disregard it because it's not going to give us any information. Page 379, in Things to Think About 24.5, you suggest trying to see what the functoriality of the tensor functor does. I think it shows that you can tensor and then compose and get the same thing as composing and then tensoring. Correct. Would you say that tensoring and composition commute? Or is there another name for this concept? I would say that they commute. There is the potential for that to be ambiguous, but if you type check it, then I don't think it is ambiguous. And so, yes, I would call that commuting. Okay, page 386. Could you please go over the subtle bits of the Eckmann-Hilton clock, or even more of 24.11? Okay, I love the Eckmann-Hilton clock. So 24.11 said, see if you can work out what each isomorphism is as you move around this clock. Okay, so I will do a quarter of it because every quadrant is the same. So we start with alpha, beta, and then immediately we insert some vertical identities. So this is, the first move is vertical identities. Then the next thing we do is interchange. I haven't really spaced this very well. And then to get to 12 o'clock, something interesting happens, because what we do is horizontal identities, but something subtle is going on because these things don't have the same shape anymore. Look, the top is a composite of two one cells here, but here it's only a composite of one cell. And this is where it becomes really important that these are both identities. Everything, all the one cells are identities, and that we're in a strict two category, because in a strict two category, the source of this is the identity composed with the identity, which is in fact the exact same as the identity. But if we were in a weak situation, this would not be the same as that, and we would have to insert some kind of extra thing to make to mediate between this composite of identities and the identity. And so when we go into higher dimensions and we do it weakly, we have to be kind of careful about that. So that is a subtlety about that. Okay, good. Page 388. Along the lines of the footprints in the snow idea, is it reasonable to think of degenerate categories as if they're projections from non-degenerate categories? Yes, as long as you don't think of projections too technically, because they're not really projections, they're really more like sort of traces of the remains. You're not actually projecting. Projecting has a technical mathematical meaning, so we should be careful about using that. I mean, trace also does, so we should be careful about using that. Okay. Would you mind, please, to compare and contrast the second square on page 391 with the second square on page 331? I think this is about cubical shapes. Right, yes. So this is about whether we have two cells that look like this. So actually, the one on page 391 is talking about double categories. And in a double category, these are horizontal one cells and these are vertical one cells, and those can be different things. Whereas on page 331, I was talking about having a natural transformation that's a square shape, in which case we would need functors coming down here as well. And those are more likely to be the same thing, because I wasn't saying that we would need a different type of functor, although I did say vertical in quotes. It would be more that we would have to use some functors to make a square shape. So there is given any two category, you can make a double category by taking the vertical one cells to be the same as the horizontal one cells, and then having two cells that live in between these composites. But double category is a more general concept because you can have something different as the vertical one cells. Okay, next question. In the square diagram on page 391, are each of the S and T morphisms different? 391, the square diagram with the graph of C1 and C0. Ah, yes, there are a lot of S and T maps. Yes, they're all different. They have to be different because they've got sources and targets that are different, right? And so because they've got different sources and targets, they have to be different morphisms. But we often write them all generically as S and T. There shouldn't be a chance for ambiguity because they've got different sources and targets, so we know they have to be different. Okay. Page 393, you write, a set is a category with no non-trivial morphisms. That is, all the morphisms are identities. Is this the same as a discrete category? Yes, yes. The technical word for a category where all the morphisms are identities is discrete. Page 394, I thought with higher dimensional categories, you start with the weakest level at the bottom and get increasingly strict, going from equivalence to isomorphisms to equalities. But you're saying that for infinity n categories, you don't start with equalities that you then have to weaken to isomorphisms when you go up a dimension. The order of weakening seems to be reversed. I think there's some confusion here between moving up dimensions inside our already higher dimensional structure and increasing the dimensions of your entire structure. I'm talking about increasing the dimensions of your structure. So if you increase the dimensions of your structure, now everything has an extra dimension to work with. So all your cells in your previously existing structure have now become more strict than necessary with respect to the external higher dimensional structure. So that's why we need to make them weaker when we increase the dimensions of the total structure. And finally, gosh, it's the last question. Epilogue, could you please say more about the clause after the colon in the last sentence of the reasoning section? And we'll give an example. So the epilogue says, in the reasoning, we use diagrammatic reasoning to make use of geometrical intuition. Proofs are often essentially type checking. We invoke the obvious axioms, which might seem obscure, but once you understand the principle, it's less obscure. The principle is that if we have two inherently structural ways of mediating between the same things, they should be the same in order to prevent structural incoherence. Yes, so I can give it, it's just like with associativity, right? If you have, we have two ways to use binary operations to put three things together. One is that we put these two things together first and then those, and the other is that you put these two things together and then those. And because those are two inherently structural ways that are different, we may want them to be the same, and that's where associativity comes from. Now, if we go up a dimension, then we don't want those to be the same, but we want there to be an isomorphism between them. And now we have different ways to get around. Wait, did I draw this diagram anywhere? Surely I did, but did I? Well, did I do the pentagon somewhere? Maybe I did, maybe I didn't. So then you can say, if I have four things, then there's a bunch of things I could do, right? I could start with the binary things all on the left, but now I could use this isomorphism to get myself to move that B branch over here. And now I could use that isomorphism again to move that composite BC branch over there. And now I can move that C branch over, and I'll have achieved getting everything associated on the other side. But there was another way I could have done it. I could have used the moving of the branch. I could move the C branch here, and that will get me to here. And now I can move the A branch over there, and that'll take me to there. So these are two ways of mediating between those two ways of associating. And so because those are two, as I called it, structural ways, what did I call it? I called it two inherently structural ways of mediating between the same things. They should be the same, because otherwise there would be some structural incoherence, like a hole in here. And so that's what I mean by that. And that is the last question. And so I think it's time for a celebration. Hold on just a moment. I'm going to stop the share and I'm going to pause the recording and we'll celebrate. So we made it to the end. It's been amazing. It's been epic. It's been illuminating. It's been rewarding. It's been hard work for everybody. And so I think it's time that we had a celebration. So I'm going to open a bottle of champagne and I'm going to specially thank everyone at the Totality Institute, especially Juliet and Tim for helping with organizing the questions and editing the videos. Brendan for being the point of contact for getting this all started in the first place. And you all for following along, asking questions and making it to the end. I'd like to thank the sunshine for being out today. And thank you to CUP for publishing this book in the first place. Thank you to whoever invented champagne. Thank you to whoever invented insulated champagne flutes so that I can drink this outside in the sunshine. And let us, if you would like, raise a glass of anything you like to the joy of abstraction, which illuminates our thinking, just like the sunshine illuminates the world around us. Thanks, everyone. Cheers. Oops, I just realized I was going to read the last section of praise and appreciation before going. So we'll have a little epilogue extra session now. Praise for the joy of abstraction and for me. I always thought abstraction got a bad rap as something lifeless, a pale imitation of concrete reality. But that can't be right. People live and die for ideals. Abstractions are active things in the world. Not only does abstraction come alive here, it actually leaps out at the page and grabs you, taking you where the chapter goes. Thanks. Bravo, Professor Cheng. Please continue writing books like this and doing book clubs with them. Outstanding job. You know, it's been really exciting, and I don't know if there are many examples of this where there's a book club where everyone can ask questions chapter by chapter and you just work your way through all the way to the end. And I think it's been great. And if there's another book written by someone who likes making videos, then maybe you can put in a request to the Topos Institute that they support somebody else to do a similar kind of book club. Thanks for giving us a safe space to ask questions. It has been incredibly helpful for my understanding. I'm so glad. Thank you so much for everything. I'm now happily enlightened about higher category theory. Thank you so much for this book club and to everyone who made it happen. Yes, indeed. Thank you so much for all of your patience and dedication and for having a great attitude. Thank you. Thanks. We made it. Hooray! That was what someone else's comment. I'm quoting them. We did make it. Hooray. The sun is still shining. We are still being illuminated. And what next? What next? Indeed, there is always something next. Onward and upwards. Bye.